I will often draw the parallel plate capacitor structures similar to the one we're looking at right here. A voltage is applied across the plates, and I show horizontal lines of electric field intensity. The voltage drop across the plates is minus the integral from the plate at D to the plate at 0 of E dot dl. But this voltage is independent of the path we take. We don't have to take a path just through the inside of the capacitor. We could take the path anywhere outside, and we have to get this result. So the electric field intensity cannot be 0 outside the capacitor. We refer to these fields outside as fringing fields. We would like these fringing fields to be negligible so that we can treat the capacitor as if the only electric field lines are the horizontal electric field lines inside the capacitor. So that I have room to illustrate what's going on between the plates, I draw the capacitor with a lot of separation between the plates. But in order for what we do in class to be valid, our capacitor structure is more like this. We are going to think of close spacing between the plates and very large plate areas so that we can ignore the fringing fields that do occur outside the capacitor. So the amount of fringing fields is negligible compared to the amount of field in between the capacitor plates. When we integrate minus the integral of E dot dl from the right plate to the left plate outside the capacitor, we are traversing a much greater distance, and so the electric field intensity will be much weaker outside the capacitor than inside the capacitor. So for maybe 99% of the charge on the capacitor, the resulting electric field lines are these horizontal lines between the plates. For problems we look at in class, I will draw our capacitor structures like this for illustrative purposes, but I will state to ignore fringing fields. When I state to ignore fringing fields, I'm implying that the capacitor structure is really more like this, where you have narrow spacing between the plates and large plate areas.